join us to talk about TFA, which is a short chain PFAS, and how that is specifically linked to the heating and cooling industry. Professor Kaufeld was awarded the Person of the Year award at a recent conference, Atmosphere Europe, back in November. Really recognizing his thought leadership on natural refrigerants and on PFAS issues. So he's a professor at the University of Applied Sciences in Karlsruhe. Is a member of many different organizations globally, from the Montreal Protocol, the different committees of the Montreal Protocol, advising the members of the countries that are members of the protocol, as well as a fellow of ASHRAE and many other organizations, professional organizations around the world. So he is highly knowledgeable in this space, and we're really happy to have Michael join us today. So without further ado, I hand over to you, Michael. I will mute myself, and I think you need to unmute yourself.
Yes. Welcome, everyone. And let me see. Mark made a nice introduction. I hope you can see my slides. There you see a picture of me in front of some water. And actually, there are some claims that the TFA in the oceans is natural resources and it's very low concentration. But once you analyze the foam at the beach, there's a lot of PFAS. The PFAS concentration in the foam is many times higher than what is in the water. And actually, there are places in Denmark where I often am, where it's recommended that you rinse your dog if the dog has been playing in the foam along the beach. Okay, let's start. I have been working with refrigeration a little longer than Mark, 20 years more than Mark, I think. I started in 1986 at what back then was called NBS, and I got my PhD in Hanover, at the University of Hanover, on air cycle refrigeration. Then spent 2 years working for hydroaluminum, mainly focusing on CO2 for car air conditioning. Then I was 8 years at the Danish Technological Institute, where our philosophy was from the beginning when I joined to focus on natural refrigerants and don't do anything else but work with natural refrigerants. 2002, I was appointed professor at the Karlsruhe University of Applied Sciences, keeping my focus on natural refrigerants and on ice slurry. In 2008, I went for a research stay to Danfoss to learn more about the smart controls, and I taught them a little bit about microchannel heat exchangers. Back at the university, I realized that young people are no longer interested in technical subjects. They don't want to study engineering. So I initiated our Inspiring program, where we send our students to the schools, to the high schools and elementary schools, kindergartens, to inspire the school children to study engineering. And in 2020, I was for a 6-month research stay at Advancer, working with CO2 as a refrigerant. And as you can see here, member of UNEP RTUC since 1997. I actually joined in 96, but officially 97. Okay, let's go to our subject. The first publication we made was in 2021. My wife and I, on open access government, on the issue of HFO and TFA. And as of last year, we got a very small Swiss-funded research project looking at PFAS-free heating and cooling solutions, especially directed towards the heat pump industry. If you look at the refrigerants used in the Swiss heat pumps, then the majority used, this is 6 years ago, used the 410A, and 50% of 410As is 125, which is a PFAS. So on the right side, you can see why F-gases are a problem. The first generation CFCs and HFCs, they depleted the ozone layer. The second generation, together also with the first generation, contribute to global warming. And now with the HFOs, we have this acidification of our water. common for all of them is if you burn them, you get some very nasty fumes. So it's not so safe to do that, to braise or weld on the system with an open flame if there are those gases around. Now, if you look at ozone depletion, we have the Montreal Protocol and the different amendments. We can say that most of the CFCs and HCFCs, they don't last longer than 100 years. So after a couple of decades after phasing them out completely, the ozone layer should restore. If you look at the global warming, the HFCs, like 134A, for example, has an atmospheric lifetime of less than 10 years. So this is solved after a couple of years after we ban them completely. The problem with HFOs is they are designed to break in the atmosphere very quickly within a couple of days, which is nice. That's why they have a very low global warming potential. But several of them, they create TFA at a fairly high rate in the atmosphere. And this TFA, once it is in the water, stays there for thousands of years. So this TFA is a forever chemical, and also certain HFCs and HFOs are fall under this list of forever chemical or PFAS. You have probably heard about PFAS in other areas, like for example, outdoor clothing or the waterproofing spray or the baking paper you may use at home, ski wax. They're all either still contain PFAS or they used to contain, or the frying pan, if you have a Teflon coated frying pan, it's also PFAS. Now, there is this nice graphic showing the environmental impact of PFAS from the manufacturing of the raw material over the product manufacturing and then the product use and the waste management. And and then you can see here emissions by air, soil or to water, and the exposure of the different people or nature. And I added another one with TFA, and we have that everywhere. Yeah, the manufacturing of the refrigerants, the product manufacturing when it comes to the air conditioning or heat pump system, the use of the system, especially car air conditioners are quite leaky. So there's a lot of 1234 YF emissions. And then at the end of the product life, there may again be some TFA formed. Now, TFA, there is a discussion, and depending on whom you talk with, the US EPA is currently not classifying TFA as a PFAS. EU is, and also the OECD, Organization for Economic Cooperation and Development, is classifying TFA as a PFAS. And last year in March was a document signed by 171 scientists also stating that TFA is a PFAS. Do you see the molecule down in the lower left-hand corner? It's very similar to this molecule, and this one PFOA has been studied extensively. Also, the impact it does on humans. And if you compare the two molecules, you remove the middle part of this PFOA, you get TFA. So TFA is the very shortest version of this kind of PFAS family. Now, there are some discussions going on LinkedIn, where I'm also involved. Some people claim that TFA is not toxic. I don't know the right definition of being toxic, but I mean, the consequence if something is toxic is that you die. And if you look at the data safety sheet from various companies, I just picked one of them, and then it says what is highlighted in yellow, if swallowed, the pure TFA, then the danger of perforation of the esophagus and the stomach. And as far as I know, if you don't get medical treatment, this will also lead to death. So maybe it's not poisonous in the classical definition, but in the end, it's the same result. You will die if you get too much TFA inside your body. And this is the pure TFA, yeah. So be aware, this is not the concentrations we see nowadays in our drinking water. Now, the effects of PFAS on the human health. You have here or a figure from different publications where it can affect the human body. And Hans-Peter Arp, a Norwegian researcher, together with some other colleagues, published a paper last year where they say the TFA might be toxic for reproduction. And then you can think of, okay, we are 8 billion people on this planet. This is too much. So let's have more TFA in the drinking water. Let's all get this toxic reproductivity so we cannot make children anymore. But I don't think this is very good because also all the animals are drinking TFA contaminated water, and then also all the animals will not be able to reproduce. And it also exhibits liver toxicity. This was tested on rats. Of course, there are some people saying that you cannot transfer what was tested on rats to human beings, but oops, I would say be careful. Yeah, precautionary principle. We have seen this before. Just take this blood-brain barrier with microplastic. We now have investigations of human brains where there's a lot of microplastics in the brain, where previously people were saying, oh, this will never happen because there's this blood-brain barrier. Or you take the tobacco industry, they have been for decades saying that it's safe to smoke. And I think, or I'm afraid that we will see something similar with TFA in a couple of years. And the problem then is that TFA is a forever chemical, so it will stay in the groundwater forever. How does it get into the groundwater? We have all these different emission sources. And of course, you could say our refrigeration systems, heat pumps, air conditioning systems, they should be completely tight, no leakage. But experience shows that the leakage rates are anywhere between 1% and 10%. In some countries, even higher. Then the HFCs or HFOs, they go to the atmosphere. They degrade to TFA at certain rates and then deposit on the soil, on surface water, and eventually on the ocean. And what is not shown here is below. We also have something called groundwater, and we even find TFA nowadays in groundwater. Actually, they have to close down several groundwater wells in Denmark now due to too high PFAS levels. Where does the TFA come from? Here you see some measurements from Switzerland. Blue are measurements close to Zurich, where you have a lot of refrigeration air conditioning systems, where you have a lot of cars, and they just cut off the scale. So this is much higher. In order to show the bars of the orange measurements, these are from Jungfraujoch, and so you can see how it's increasing over the years. So here around 2010, 2011 was the market introduction of HFOs, and we see a nice increase of the concentration of the HFOs in the atmosphere. Now, if we go to TFA, this is a publication from Germany. This is from 2020. There are newer measurements, but this graphic is fairly nice. You can see here, this is from emissions, TFA emissions from 1234YF. This is from 134A. 134A converts about 20% to TFA, whereas TFA is 100%. HFO 1234YF results in 100% TFA. And then you have some other sources. Now, looking at the refrigerants, here's a list of the various refrigerants. Be aware it's only refrigerants with a GWP below 750, because in Europe we have this F-gas regulation, and you're not allowed to use refrigerants with a higher GWP anymore. But there are other refrigerants, fluorinated refrigerants with higher GWPs, which are also forming TFA, but they're not on this list. And the number one source is 1234YF, which is unfortunately used in almost all car air conditioning systems. And the consequences of that we will see in a couple of slides further down. Now, this is from a recent report from UNEP, from this assessment panel for looking at the environmental consequences. And you can see here how much TFA is coming from the refrigerant. Here we again have 1234YF, so it's 100%. The same is true for this substance, or up here at 124. 134A, the previous refrigerant for car air conditioners, is only 20%. But the amount emitted, This report is from 2022, published in 23. So the data are probably from 2021. And of course, 134A emissions are the highest, but only 20% TFA yield from this. Back then, a couple of years ago, 1234YF was much less than 134A emissions, but this converts 100% to TFA. It's approximately the same. If you multiply this by 0.2 in the 134A bar, you get the same amount of TFA. And nowadays, it's more from 1234YF. The other thing is, or the difference is that 134A has a very long atmospheric lifetime. So wherever it breaks down into TFA is not at the point of emission. It's somewhere else on this planet. It can be in South Africa, in Australia, in Brazil, wherever. Whereas 1234YF breaks down within a couple of days. So it also settles on the surface, on the ground, and on the surface water, very close to the point of emission. In the summertime, if there's no wind at all, you take the valley of Stuttgart in Germany, where you have 800,000 cars, all emitting 1234YF, no wind for 2 or 3 days. All the TFA will deposit just inside of Stuttgart and along the hills of Stuttgart. Now, since I'm living in Switzerland, I took Switzerland as the first example. These are measurements of TFA in groundwater in Switzerland. And unfortunately, also in surface water. You can see here some measurements in Swiss lakes. The concentrations are quite high already. Unfortunately, most of the lakes are used as a source for drinking water. And because there's no way of removing TFA from the drinking water with the current technology, we have the same amount of TFA in the drinking water. Actually, we here in Rapperswil, we have about 600 nanogram or 0.6 microgram per liter. And we also find TFA in beer. As being from Germany, I'm very fond of beer and also drink it myself. But if you take the German purity law, they have to modify it because there's also PFAS in the beer nowadays. Actually, they tested 104 beer samples from 23 countries, and you can see here you had as high as 51 microgram per liter of beer. I don't know which brand it is, but I wouldn't drink that kind of beer any longer. Now, if we go to Germany, since University of Karlsruhe is in Germany, we are located down here, Karlsruhe, very close to France. And these are the measurements on the left-hand side of surface water and then groundwater on the right side. All the white areas are not white because there is no TFA contamination. There are just no measurements so far, or no published measurements. That's why it's white. You can convert these maps into something looking like this. This is for rivers. So the surface water, the median concentration is the left one, and then the maximum concentration you have here on the right. And then you see here, this is the Rhine River, and this is the Elbe River. So along the rivers, you have a very high TFA concentration. And with groundwater, you also see there are some hotspots in Germany, here around this area, and then down here or up here, where there's already a lot of TFA in the groundwater. What does it mean for our drinking water? Here are some measurements published, I think, last year for different drinking waters or tap water. Now, these are just numbers. They range up to 4,100. And this is in nanogram per liter. And for mineral water, they analyzed several mineral waters. And you can see one of them has 3,200. Several of them, I guess all these like B, A, Q, T, and so on, they are from very low levels of groundwater somewhere in the mountains. Now, the EU has proposed to have a total PFAS limit of 500 nanogram per liter as effective as of 12th of January next year. If you classify TFA as a PFAS, then several of the tap waters and at least one of the mineral waters is way beyond this limit which the EU will have. Leading European tap water suppliers, they recommend that for substances which are not yet fully evaluated what effect they have on the body, the limit should be 0.1 microgram or 100 nanogram. If you draw a line of 100 nanogram, most of the tap waters on the left-hand chart, they are way above already. So they have to introduce new means of cleaning the water. We tested ours in Karlsruhe at the university and then at our partner university in Rapperswil. You can see they're both well beyond the limit which is proposed from these leading European tap water suppliers. So in conclusion, we can say for some of the waters, it's already too late. Of course, you can say, okay, we just raised the bar. We say the limit is not 100 nanogram, but 1000. And then in a couple of years, we raise it to 10,000. The problem is once we find out that it does something to our body and to the bodies of all animals, it's too late because we cannot remove it from the water. It will stay in the groundwater for thousands of years, which is many generations to come. So it's not only something for us and our children or grandchildren, but it's like, I don't know, you have to say 50 times grand to get to the generation in 1,000 years. If you want to remove it, this is from a publication or a citation of various American sources because they're also focusing a lot on PFAS nowadays, even though the EPA says TFA is not. The waterworks are thinking about it, and you can see here this Steve Weir, who's the manager of the Federal Relations for the American Water Work Association. He says that the current filtration methods cannot remove PFA because activated carbon treatment will not do it, remove it. What you would have to do is reverse osmosis, but this also removes all the minerals, and then you have to remineralize the water. So this is going to be very energy intensive and very expensive. If you ask me, I think we should try to avoid this as much as possible. This is a German study showing PFA in on the left-hand side. It's the TFA with different sources which they believed or were sure in 2021 where it comes from 8 meteorological measurement stations spread out across Germany, as you see here on the map to the right. And they have a very conservative approach and say that this part, the purple red colors, this is from refrigeration, and the green part they don't know. But what is interesting is what is written here, the citation at the bottom, that we have a 3 to 5 times higher TFA content in the rainwater nowadays than what we used to have 30 years ago. And if you already now try to imagine the rise of the sales in HFCs and HFOs over the last 30 years, there might be a link, which I will show on the next couple of slides. These are ice core measurements, and you can see here no HFCs, just we only use CFCs as refrigerants. Then the market introduction of HFCs is around here, and the market introduction of HFOs is around here. So we see a sharp increase in the ice core measurements of TFA after the market introduction of HFCs. We also see a similar trend when we look at leaves from plants and needles from plants. Here's the time market introduction of HFCs, and then here's the market introduction of HFOs. Now, more recent ice probe measurements in Arctic regions. This is a publication from 23. You can see the number one PFAS is now TFA in those ice core measurements. Then here, you can see how it's increased over time. This is a new publication from Germany where they measured leaves far away from agricultural sites because some people, they say, oh, this is all from pesticides. But I think this proves very well that it's not from pesticides because those trees which are far away from agricultural areas, they get the TFA from somewhere else. And this goes, the increase in the leaves, TFA concentration in the leaves and needles follows very nicely the increase of the TFO emissions from 1234YF. Yeah, this is another way of looking at it. They just said, okay, pre-2010 and post-2010. So this is before HFO came into the market, and this is after HFO came into the market. And for most of the things which they analyzed, it's much more after HFO came into the market. And this is what we have nowadays. Now, the future may look like this. On the left-hand side, you have the two degradation paths. So R134A, as I mentioned before, about 20% turns into TFA. And this is happening anywhere on the planet, but not at the source of emission. 1234YF, 100% TFA and very close to the source of emission. Now, what these British scientists did, they said, okay, we take all the known 134A emissions from today and assume that we have the same HFO 1234YF emissions at the same location in the same amount as with what we used to have with 134A. And then you get this. Here's Europe. This is around where Stuttgart is. 250 times higher TFA concentration in the atmosphere. This means 250 times more in the rainwater. This means 250 times more in the surface water and 250 times more in the groundwater, in the drinking water. I don't want to drink that water anymore. We do need to think about proper cleaning methods. Now, when it comes to TFA in our homes or in our body, this is an investigation from the US made by some Chinese researchers. You can see here the green bar is the TFA, and then there's some other PFAS. In the dust, there's TFA, the most prominent and dominant one. In the water, in the drinking water, the tap water, it is. Serum is the blood of the people. And then there are people claiming, oh, it's no problem, TFA is just going through the body, you drink it and you pee it out again in the toilet. But then we should have a similar concentration in the urine, which we don't have. So what's the problem? The problem is this. This is a fairly old investigation, 1990. They injected TFA into the blood veins of some soldiers. This is not the way we take the TFA. Yeah, we usually don't put the drinking water directly into our veins, but we drink it and then it goes through the stomach and through the other inner organs before it goes to the blood. But the half-life in the human body of this investigation where they injected it into the blood vessels was 16 hours. When you drink it, it's a lot more than the 16 hours. And this is the half-life. So this is until you have removed half of it from your body. I don't know anyone who on a regular basis doesn't drink for 32 hours or 40 hours or doesn't eat for 40 hours. So it will probably accumulate in the body. Now, if we go to back to our research project, which we recently had, this little one in Switzerland, where we looked at PFAS in heat pumps. This is a typical heat pump from the manufacturer who joined the project. And you can see all the different places where there are PFAS. And we analyzed the system. In total, on a weight basis, PFAS is only a small percentage of the heat pump. And the main fraction is the refrigerant. We will see on the next slide how much it is actually. But in the environment, 60% of the PFAS is from refrigerants. And most of the rest is from pesticides. Now, in case if you are a technical person and you are working with manufacturing, here are some of the trade names and the abbreviations of PFAS containing polymers. So you could ask your supplier what they are using, and then you can screen the components and say, okay, I don't want this anymore, I want something else. In case you're in doubt or the supplier doesn't tell you, there is a possibility of analyzing it. Many laboratories can do this. For example, this one in Switzerland, they can tell you if your solid components contain PFAS. We did this for the heat pump for one particular heat pump model. It's for a multifamily house. It provides 30 kilowatt heating capacity. It's an outdoor air to water heat pump. Total mass is 800 kilogram, 22 kilogram refrigerant charge, 410A, 11 kilogram, half of it is 125, which is a PFAS. The other half is R32, which is not a PFAS. The remaining 400 gram are the solid particles in this heat pump. For example, down here you have the compressor. This compressor has a side glass, and the side glass has an O-ring, and this O-ring contains PFAS. And of course, there are also, during the production process or manufacturing process, PFAS involved. Now, if you look at the numbers up here, it's like 11 kilogram is the refrigerant PFAS. 400 gram is the solid particle. The refrigerant is prone to be emitted to the atmosphere, depending on the application and depending on the country. Whereas the solid particles, they can usually be quite well recovered and recycled at the end of the product life. Now, you may have heard about this REACH proposal in Europe. It was submitted last year, or actually 2 years ago, 23, by 5 countries: Germany, the Netherlands, Denmark, Norway, and Sweden, to have about 11,000 different PFAS, or around 10,000 it says there, excluded from the market. And the hearings will be next month in March, of all the thousands of claims by industry why this is not possible. In case you wonder what REACH regulation is, on this slide you have the background. It was introduced in 2006 to protect the people in Europe and also wildlife from harmful chemicals. So I think this with TFA would fit very well under this REACH thinking it. Now, PFAS-free is possible also with solid components. This is an example from the outdoor industry, Baudet, and they will this year remove PFAS from their very last product line, which are tents. In everything else, they have already removed PFAS completely. Examples or other examples of PFAS-free frying pans. You can use stainless steel, cast iron, or ceramic coatings. They are PFAS-free. The same is true for ski wax. PFAS-free is available now. PFAS-free PV panels. The backside of the PV panels often contain PFAS. This can be made PFAS-free. You can even make lithium-ion batteries for the cars PFAS-free. There's the first prototypes are tested in real life inside the cars. And you can also make cooling systems PFAS-free. This is a nice example we had at our university. It's a solar-driven steam jet ejector air conditioning system. We produced about 80 to 100 kilowatt of cooling capacity for a large laboratory building. By only using the energy from the sun, we simply produced steam, 140 degrees hot, almost 4 bar pressure inside these vacuum tube collectors, went through this steam jet ejector, which was connected to the evaporator, and we produced 12-degree cold water, chilled water for cooling the building. The nice thing is that all these things here were from the chemical industry. So all the gaskets were PFAS-free and all the components were PFAS-free. So this was actually a system which was almost entirely PFAS-free, maybe except for the electronics. Another example is our current project, EU project, for African hospitals, where we provide them with refrigerated containers and with systems to clean their drinking water. If we focus on the refrigerated container, we do have a propane system here in the small machinery room. Then we have heat transmission via CO2 loop to ice banks. So instead of having large amounts of batteries, electric batteries, we just use ice thermal storage. This is the room for medicine and ointments or food at +5 degree. And then they have a -30 degree room here for blood plasma and other things. And we provided them with a small freezer for vaccines, which may need to be cooled down to -70. And it's all powered by PV. So the sun is doing the job. And we can bridge up to 32 hours. So a full day without sun is no problem. In case there's a longer period without any sun, we can either connect to the grid or we have a small diesel engine gen set inside. So these are examples for where at least the refrigerant is completely PFAS free. Here with the container for Africa, I wouldn't claim that the compressors are, because we still have those side glasses with O-rings, and also the power electronics are with PFAS. For the refrigerant, there are PFAS-free refrigerants, and you see them here: ammonia, CO2, propane, propene, isobutane, pentane, other hydrocarbons, water or air in the air cycle, whatever you want. Propane was actually introduced into the market 100 years ago as the odorless safety refrigerant, as compared to toxic refrigerants. I mean, I wouldn't take breathe the propane like some teenagers do to get high, because if you then have a source of ignition, then it was the last breath you took, and it will look quite nasty, what is left over from you when your lungs explode. If you take the German refrigerator industry, this is how they changed. 1991, everything on CFC 12, market introduction of 134A. A few manufacturers changed to isobutane, and then within just 4 years, the entire industry converted to isobutane. This is 30 years ago. Happened to the household refrigerator industry. We see the same thing all over the world. Even in the United States of America, they nowadays use isobutane in the household refrigerators. And I think we will see the exact same in the heat pump industry, except they will use propane instead of isobutane. And of course, it's 30 years later now, but this is going to happen right now in the heat pump industry. Talking about heat pumps, this is a nice example from 2 of my students. They invented a hot dog heat pump because they said we have to cool the beer or the beverages. So they made a nice water bath here for the beverage bottles, and here's the water bath for the sausages. And then in between is a heat pump working on isobutane, -2 degrees evaporation temperature, +90-degree condensation temperature. And with 385 grams of isobutane, they achieve a COP of 3.5. And within 45 minutes, they can cool down 35 beer bottles and then heat 3 kilograms of sausages. And because they are students, they made this experiment themselves. And then they found out, okay, after some time, they're not hungry anymore, but they're still thirsty. So they introduced an air-cooled condenser. So they can always cool the beer bottles. They don't have to eat sausages while drinking the beer. This was their project presentation some years ago. Ammonia is another nice natural refrigerant, and the very nice thing is that it stinks. You have a built-in leak detector, which you don't have for hydrocarbons, unfortunately, but we are working on it. We will have very soon a research project where we will develop some odorant for hydrocarbons to be used in refrigeration systems safely, so that people can smell if there's a leak. Ammonia achieves the highest COPs of all refrigerants. Low charges are possible, and examples are many around the world. Here are a few from Denmark. Shopping, what is the department store air conditioned with ammonia, a conference center air conditioned with ammonia. They even use this in the ammonia in the International Space Station because ammonia has the best thermophysical properties. And we are currently have another project where we work on environmentally friendly cooling of data centers, and we are also looking at ammonia, putting ammonia in not in direct contact, but very close to the computers themselves for cooling them, because it's the most efficient refrigerant. Now, CO2 is another one. CO2 is, at least in concentrations below 10% in air, non-poisonous, and it's non-flammable. It's actually used for extinguishing fires. And here is from a recent atmosphere publication, the number of the CO2 systems. And I'm old enough that I still know the very first systems. I visited one of the first CO2 supermarket systems in 1998 in Switzerland. And nowadays we have over 90,000 in Europe. and it's still growing. You can see here we have a nice market uptake in Europe, and Japan and US is following, just with a little time delay, similar to the household fridges. CO2 can also be used for district heating systems to replace big power plants, coal-fired or gas-fired power plants. This is an example from Denmark, a Swiss manufacturer. They are almost ready to start the system. They're almost done with the installation. It's a 70 megawatt capacity heat pump. If you take your car, if you have an electric car and you have a heat pump in your car, the capacity of the heat pump in your car might be something like 5 or 6 kilowatt. So this is 70 megawatt for the city of Esbjerg, all taken from the heat from the North Sea, and then elevated up to the district heating system. In Aarhus, they do it with 2 different refrigerants. They have an ammonia water cascade system with a turbo compressor for the water part, because water has very low pressures at these temperatures, and you need a very large swept volume to work with it. And then, for the technical affine people, listeners, here's how they made this layout with the ammonia. That greens the ammonia system, the ammonia heat pump, and this is the water heat pump, and the two are on top of each other to achieve this temperature increase. Last slide on the technology. It was the subject of my PhD, as I mentioned in the very beginning, air cycle refrigeration. Nowadays, there are companies manufacturing this for low temperature applications below -50. There's no need anymore for exempting the low temperature applications from the F-gas regulation. There are systems available which works much better than the R23 system with HFC. And this air cycle system, I made measurements on the system, is more energy efficient, and it's completely environmentally safe. I mean, you cannot die of too much air. With all the other refrigerants, of course, it depends on the concentration. You can even die with water if you have too much water in your lungs. Now, a few slides on this, the solid parts. This is from last year's what is called a Till exhibition in Nuremberg. Various manufacturers claiming that they have natural refrigerants, which is true, and one of them says PFAS free. And then the question is, yes, is their system really PFAS free? And if you look at the system more closely, it's not, because they are using O-rings, but there is a possibility to get rid of the O-rings. You could just use flat gaskets, which are available completely PFAS free. There are also PFAS free shaft seals. There are also PFAS free coatings for the electronics, for the evaporator. So it is possible. It's just a matter of will. Do you want to do it? If you want, it's possible. And we saw a nice example at this atmosphere conference in Prague in November last year, which Mark mentioned. Yeah, this is an Italian manufacturer. They have all their O-rings PFAS free. So it is possible. Yeah, you can do it. You just have to want it, and then it's feasible. Now back to the refrigerants. This is Mark McClinton, one of my very first colleagues in 1986 in Washington, D.C. at NIST. Mark made an investigation with some colleagues. They looked at 60 million different chemicals, and their conclusion was, after HFOs, there's no more. And this is the challenge we face right now. Both DuPont has branched off their refrigerant business, or the entire fluorinated thing, into Chemours. Honeywell did the same last year. And those daughter companies focusing on the manufacturing of fluorinated refrigerants, once the HFOs are prohibited, they don't have any business anymore. They will have to close or have to find other things for getting rid of their fluoride, maybe in toothpaste. Now, if you look at the efficiency, but some people question the efficiency of the natural refrigerants. This is one graph from Mark McClinton, and measurements on real systems and experience working with real systems underline this. The best refrigerant, if you have an internal heat exchanger, are the hydrocarbons. Can make the exact same thing without internal heat exchanger, then ammonia is on top. And the very nice thing about the natural refrigerants are the CO2 equivalent manufacturing emissions. You can see here the blue bars, ammonia, CO2, pentane, and so on. And this is 1234 YF. It's 10 times more, 11 times more than the natural fluids. 134A was 4 times more. So there's no environmental drawback of switching to the natural refrigerants. And my own HFO personal view is this. This was a slide I prepared for a presentation at the Euroshop trade fair in 2017. And then people took out their cell phones to make the calculation, and some of them were still smart enough to do it in their head. But it's not the calculation I want to show. I say it took 60 years to find out that CFCs damage the ozone layer. It took 30 years to acknowledge that HFCs contribute noticeable to global warming, and it will take 15 years to accept that HFOs are harmful to the local environment. This was 2017 plus 15, so this is makes it 22, 32. By 32, hopefully we get rid of HFOs. And if you look at it on a worldwide basis, with the CFCs, we damaged the ozone layer 20 kilometers above the surface. With all the fluorinated refrigerants, we contribute to global warming, which is the lower 20 kilometers of our atmosphere. And now with HFOs, we damage the ground. So well done, refrigerant in this industry. Simply contaminated or affected everything from 30 kilometers above the surface of our planet and now even in the ground of our planet. So for a conclusion, you could have a look at the cover of the Applications for Natural Refrigerants Conference 1996, which I organized together with my colleagues from DTI in Denmark back then. And I designed this logo, and I said, okay, the green arrow are all the natural fluids, and then out to the right you have the CFCs, the HCFCs, and the HFCs. And back then in 96, people were saying, no, they are crazy, those Danes. The former Minister for the Environment, Sven Auken, he had the opening talk, and he said that within the next 10 years, 96 to 2006, he wants the Danish industry to get out of HFCs. And even though there was a complete shift in the government from Social Democrats to conservative parties in 2001, they kept the promise. 1st of January 2007, it was prohibited to use HFCs in larger refrigerant and air conditioning systems in Denmark. And if you look at the industry nowadays, many of the leading companies manufacturing natural refrigerant systems, they come from Denmark. And why is that? It's because they were forced to do so 15 years ago or 20 years ago. So my prediction for a new logo, if you had to make this conference again this year, I would just say CFCs and HFCs. HCFCs are together, HFCs, and then HFOs would be the third arrow out to the right. When I was a teenager, I was very happy to play the pinball machine. I always asked my parents for some money when we went in a restaurant where they had the pinball machine. And no matter how much money I got from my parents, in the end, I always lost the ball. And this machine said to me, game over. And this is my personal view on the HFOs. I think for HFOs, we will see this game over, hopefully sooner than later, because once the TFA is in the groundwater, it will not disappear by itself. And we can install the technology to make our drinking water free for TFA again, but what about all the animals? They cannot just install filters. Because we have a special day today, the Valentine's Day, I created this logo this morning. Natural refrigerants, be my Valentine. Thank you very much for listening. Here are the contact data for myself and also for my wife. the other partner university in this project. And to the right, you see the cover of a book, Natural Refrigerants Applications Guideline. The nice thing about the book is that the entire revenue of the book goes to the benefit of our students. So the publisher, VDE, they donate all the money to a foundation which is supporting our students. So thank you very much, and I'm open for questions.
All right. Thank you, Michael. A very interesting presentation. I'm conscious of the time. We have about 4 or 5 minutes. We'll run a little bit over if people want to stay on. I see in the chat that there are several questions, so let me go through some of those. There's a first question about the hearings that you referred to in March. I can answer that one. That's for the REACH agency as part of the ECHA process, the PFAS restriction proposal. They're having meetings every 3 months, and the next scheduled meeting is first and second week of March to look, and they will be looking at refrigerants and transport for the first time. So hopefully that answers your question, Mas. And then I see you had a second question. What is Michael's view on solid state alternatives such as shape memory alloys?
For refrigeration systems.
Yeah. Yes.
Yeah. It's funny. Last year I think it was September, I made a seminar for a large manufacturer of natural refrigeration or natural refrigerant systems, and they were also thinking of the future, and they asked me, okay, is there a game changer like we have seen for watches? Yeah, earlier watches were mechanic, and now we all have quartz watches. Or you take the light bulb, the Edison light bulb. Nowadays we have LED lighting, much more energy efficient. And with a colleague of mine, I analyzed all the different things which are discussed and investigated right now. We don't see any game changer yet. It might become, there might be something coming up. But if you, for example, take Peltier elements, this electric cooling, which is used for small boxes for your car, they are brilliant if the temperature lift is very small. So for 1 or 2 Kelvin, you get a very high efficiency. But if you want 30 or 40 Kelvin temperature lift, efficiency is very poor. Magnetic refrigeration, there have been demonstrators, but so far there's nothing like really commercially available on a big scale. Stirling cycle, there are various things, also these phase shape memory alloys or elastocalorics with some rubber elements. I mean, there's a lot of research going on, and I will not say that it's not possible because we have seen it with the watch industry, we have seen it with the light bulb industry. Maybe we see it with the refrigeration industry as well. I don't know. Will be interesting.
Yeah, but in I mean, these other types of refrigeration systems and technologies, they're where maybe say natural refrigerants was 20 years ago. So in terms of like the PFAS challenge that we have right now, and policymakers, if they're going to ban PFAS refrigerants at the end of this decade in refrigeration, they need to know that there are commercially available alternatives today.
Yes, and they are
at scale. And you
Yes.
mentioned, you gave some examples. You referred to a report that we just published, and something that is worth adding to what you said was that there are already tens of millions of propane self-contained cabinets in Europe today being used in refrigeration. That's quite a substantial number. So there are millions of hydrocarbon systems in commercial, and I'm not even talking about domestic refrigeration.
Yeah, and
So
you can take.
yeah.
Sorry to interrupt.
Yeah.
You can take split air conditioners. In Germany, we have this environmental seal, this Blue Angel. I mean, the only
sure.
split air conditioner in Germany is from a Chinese manufacturer because they use propane, and they have investigated it. It's 10 times more safe than using isobutane in the household refrigerator to use propane in the split air conditioner.
I want to talk also about air conditioning in cars. Could you go to could you show your slide 20 or 21, please? I think and I know there's another question also asking for slide 16, and we'll ask that question after. But I think it's 21 or 20.
This one?
Yes. No, go to 21. No, it was 20. It was 20.
This one?
Yeah.
Okay.
Yeah. So on the right-hand side, where you were starting to see these TFA concentrations start to really increase, and there you can see there's a link to refrigeration per se and not pesticides. Okay. And it's quite interesting to see that this red line on the right-hand side is starting to really take off from 2013 onwards. And it's quite interesting when you think about all the mobile air conditioning in the cars. The new refrigerant 1234F, which is this 100% TFA, was starting to get introduced in Europe, across Europe from 2011 onwards, and really started to take off 2013, 2015, 2017. And now, there are like 10 million of these models. There's 10 million of these HFO air conditioning systems sold every year in Europe. 10 million cars every single year. So, I would be interested to see how this is really taken off 2020 onwards. But there you could argue that there's quite a clear link with mobile air conditioning. So it'll be interesting to see what the studies come up with in the future about that. But the good news is, in the case of electric vehicles, there are already 1 million cars today in Europe with CO2 heat pumps. So we don't even have we don't need a PFAS refrigerant in your air conditioning for your electric vehicle. There's already 1 million commercially available today in Europe. And people, when I say that number, they're always shocked to hear it. So that's an alternative available in 2024. We're now early 2025, and bans would only come 5 years from now anyway. So we've got plenty of time to introduce new products.
The other option, Mark, is propane.
Yeah,
absolutely. There is a manufacturer from Munich now selling propane air conditioning systems for caravans. They're on the market. They're on the market.
I know. And we hosted a conference last year in Berlin, where we had Ford from the US talking about how they're looking to bring propane into their air conditioning systems as a PFAS-free alternative to YF. So there are major players looking at this, investing in this technology, and we're seeing many, many different alternatives across many different applications. Now, conscious of time, there was a question. I'm looking at the chat thing next to my screen where it says there's a question. I have a question regarding slide 16. What is the reason for the huge TFA level in Upper Austria? So I'm guessing this person is from Austria.
I don't know.
And he's concerned, or he or she is concerned.
I don't.
Do you know?
No, I don't know. I don't know what it is. So.
Okay. All right. Well, sorry.
Maybe they have using a lot of pesticides in that area, or maybe it's close to a manufacturing site where they spill a lot of TFA. I don't know.
Okay. Yes. Yeah. Then watch Dark Waters. That's what I can say. Okay. I see Cinzia added a link to presentations about the Max Summit, the one for all the different alternatives in mobile air conditioning. Thank you there, Cinzia. Then there was one other question, maybe.
I can send some papers. There was Sissel Dukier. I guess looking at the name, she's from Denmark.
Yes,
I can send you the paper that we were at the Gustav Lorentzen conference in, I think it was Edinburgh, 2016, where we had the paper on this solar system with the ejector. And again, if you send me an email afterwards, I can provide you with the paper.
So that's referring to the solar thermal ejector project, right?
Yes.
Okay. Fine. Then I see there's a comment from Marcus from Equans. With the connection to politics, how do you feel about the chances of PFAS ban? I mean, they're now starting to talk about this formally as of the March meeting. We expect that to go into June and September. And so this is the year where the experts at the ECHA, at the REACH agency, and all the national experts and industry experts will be involved. And so this is the year where people really start talking about that. And if they're going to ban anything, if they're going to ban HFOs, they will only do so if there are viable alternatives in the market. And this is what we are trying to do with the Coalition for PFAS-Free Cooling and Heating, and all the various activities that I can only speak for as Atmosphere here is also doing to try and raise awareness about all the plenty of alternatives and companies, the thousands of companies across Europe that sell products with natural refrigerants. And, Michael, you mentioned Chillventa. I mean, there were 1,000 exhibitors at Chillventa. Probably about 900 of them were exhibiting natural refrigerant products. Yes. Most of them propane, many of them CO2, and some even ammonia systems, and solid refrigerants as well as air and water. So there was a whole variety of options there that are PFAS free. And
that's a very nice story. We had the UNEP ARTOC meeting once in Jordan at a manufacturer for chillers, large chillers. And I gave a presentation after the ARTOC meeting to the entire engineering people and also the owner of the company, and told them what you have to do is you have to develop chillers with propane or with ammonia. And then just 2 years later at Chillventa, they were exhibiting, and then this chief engineer, he took me aside and said, "You know what? I show you our latest development." It was a propane chiller. And in 2018, the market introduction by this manufacturer from Jordan.
Great to hear. And there are every day new players, new solutions coming to market with a variety of different natural refrigerants for a variety of different applications. So we're quite confident that policymakers, if they receive that information, and this webinar is part of that information sharing process, they will receive, and some are on this call right now, and others will be receiving it as a follow-up, to say that, first of all, refrigeration is part of the problem because of TFA. And the good news is that we have solutions that are PFAS free. And there are many of them, thousands and thousands of companies across Europe that already sell these products daily. So we need to make sure that the policymakers hear that rather than the misinformation that we don't have alternatives, which unfortunately is quite common in our industry. So hopefully I'm answering your question, Marcus. And please, if you are engaged with any policymakers at your level, where I believe you're probably in Austria or Germany or Switzerland, please engage with them as well. Any official in any way you can, to tell them that you're working on alternatives that are PFAS free today. Okay. The question from Matteo. Could you kindly show the slide about PFAS free O-ring manufacturer? This is OLAB, Italian manufacturer, right? They got the Innovation of the Year award at the Atmosphere Europe conference last year that we hosted. And they brought a PFAS-free O-ring, and since then they've been bringing that right to the whole range of products that they have, and they see this as a key differentiator for themselves in the market, and they have developed that in a very short space of time, and so amount of time, and so we're quite confident that for that 1% of the problem, which is the PFAS that isn't a refrigerant. And there will be more and more companies coming to the market over the next few years providing PFAS-free solutions. And OLAB is an example of that. Does that answer your question, Matteo? I'm guessing it does. He hasn't answered. So, yeah. Did you want to add anything there, Michael?
No, it's just,
No.
I mean, but as I said, I mean, the real big thing is the refrigerant, and then all the solid components is like 1 or 2% of the challenge, and it's not as dangerous because they don't evaporate.
And we know that a lot of the industry, through the traditional associations that represent our industry in Brussels and beyond, are using that as a reason to not do anything because of the 1% problem. But again, let's not forget the focus. The refrigerant is the key problem here, and that links and we can fix this. All right, and we have solutions. And even on the 1% problem, we're finding alternatives already now, and that will be something that more companies will bring to market over the next years, because they will see that as an advantage to compete on. If all I put money into this and invested money into this, is because they see this as a way to stay ahead of their competition. So credit to them. Okay, are there any final questions before we log off? Looking on the chat. All right, Michael, do you wish to add anything?
No, just thank you very much for listening, everyone. And as I told our students last year at the sustainability summer school, spread the news. Like this morning, I had a very nice conference call with a former student from Uganda. He's now working for the agricultural ministry, and they want to build a new cold store, and his supervisor wants to have a cold store with HFC. And I said to Joel some weeks ago, no, I mean, you learned better last year at our sustainability summer school. And so this morning we had a meeting, and I thought it was with Joel and his supervisor, but there were like 15 people from the ministry, from GIZ and refrigeration fitters. And that they're all determined now to look into propane as a refrigerant for their cold store, or ammonia if it's a bigger cold store, but go away from HFCs.
Great news. Great news. Good. So we will be sharing this video recording on via YouTube and LinkedIn, and to people who registered to on the webinar. And so and we will also summarize some of the main highlights from this via our various media channels. So yeah, so this is very useful input from Michael, and I'm just trying to answer some of the questions that I'm seeing, Michael, here on the chat. So yeah, so don't worry, you'll be hearing about this shortly. Thank you all. Thank you, Michael. And all have a nice weekend. Bye-bye, everyone.